I am Sheikh Mahbub Basha. Welcome to my channel. Happy learning.
Hi students, welcome. Welcome to 10th class Physical Sciences. Today we'll start a new chapter, Refraction of Light at Plane Surfaces. Before that, let us have a brief discussion. The light has various properties like rectilinear propagation, reflection, refraction, dispersion, scattering, interference, diffraction, polarization, photoelectric effect, Compton effect, etc. Among these various properties, the first two properties, rectilinear propagation and reflection, were already discussed in your lower classes. Here in 10th class, we'll discuss refraction, dispersion, and scattering, and all the remaining properties will be discussed in your higher classes, that is plus 1, plus 2, and so on. Once again, under refraction, we have discussion in two parts, that is refraction of light at plane surfaces and refraction of light at curved surfaces. Then we will discuss dispersion and scattering. This chapter is meant for refraction of light at plane surfaces. Let's have a quick revision of reflection of light. There is a mirror. When a light ray incident on a mirror, a normal is drawn at the point where the ray is incident. Then the light ray reflects back into the same medium, and here the normal is drawn to the surface of the mirror at the point where the light ray incidents. The angle between the incident ray and the normal is called as angle of incidence I, and the angle between the reflected ray and the normal is called angle of reflection and is noted by R. Regarding this reflection of light, we have two rules. Number one is angle of reflection R is equal to angle of incidence I. I and R are equal. And the second rule is the incident ray, the reflected ray, and the normal are coplanar. That means the three rays, the three lines lie in one plane. This is about the rules related to reflection of light. Now let us move to refraction of light at plane surfaces. When a coin is kept at the bottom of a vessel and water is filled into the vessel, then the coin appears to be raised under the water. It appears to be raised inside the vessel under the water. Similarly, a lemon kept in a glass tumbler and filled with water appears to be bigger than its actual size, and when a thick glass slab is placed over some printed letters, then that letters appears to be raised when viewed through the glass slab. These are all our daily observations. First of all, let us do an activity. That is activity 1 in your textbook. Take a glass tumbler. Keep a pencil long enough in the tumbler. Pour some water into this tumbler. Look at the pencil first from the side of the glass tumbler. The pencil appears to be broken. Then observe the pencil from the top of the glass, that is directly through air. This pencil appears to be normal when seen from the top. So the pencil appears to be broken. It is in the form of two pieces when seen from the side through the glass, and it appears to be normal when seen from the top of the tumbler. So when viewed from two different directions, we have two different observations. Take a vessel with opaque walls, such as a mug that we use in our household bathrooms. Place a coin at the bottom of the vessel. This coin is clearly visible to you when it is viewed from the top of the vessel. Now, slowly move away from the vessel, and each time note that the coin is visible or not. The light ray originate from the coin does not reach your eyes at some stage, and you will be unable to see the coin. Now ask your friend to fill the vessel with water. The coin is now becomes visible. What could be the reason? The rays from the coin are unable to reach your eyes when the vessel was empty, but when it is filled with water, the same ray is able to reach your eye, and the coin is visible to you. The property of rectilinear propagation of light means the rays should travel in a straight line. So the rays from the coin may be moving straight in air and may be moving straight in water also. That means the light is bending at the interface of water and air. This is possible only when there is a change in the speed of the light. Therefore, the process of changing speed at the interface when light travels from one medium to another medium, resulting to a change in direction, is a refraction of light. The process of refraction involves bending of light. Look at this picture. We need to understand the terms rarer medium, denser medium, interface, speed of light in rarer medium, speed of light in denser medium, point of incidence, normal, incident ray, refracted ray, angle of incidence, and angle of refraction. We need to understand all these terms. First, let us start with the rarer medium. Here in this picture, the white portion is the rarer medium. So rarer medium means a medium in which speed of light is greater, and a denser medium means a medium in which speed of light is slower. So comparatively, speed is more in rarer medium and less in denser medium. Speed of light in rarer medium is taken as V1 in this picture, and the speed of light in denser medium here is taken as V2, that is in the green shaded area. They are not equal, right? Then what is interface? Look at this picture. There is a black horizontal line separating the white portion and the green portion, that is the rarer medium and the denser medium. The line, the plane that separates the two mediums is the interface. Next, speed of light in rarer medium will be more, and it is V1 here, and speed of light in denser medium will be less, and it is V2 here in this diagram. Then point of incidence. The light ray is coming with a speed V1 and touching the interface. At that point where the incident ray touches the interface is called the point of incidence. So normal is the perpendicular drawn to the interface. Perpendicular drawn to the interface at the point of incidence is called normal. Normal is perpendicular to interface and passes through point of incidence. Then incident ray. So the ray that originally coming is the incident ray. Then refracted ray. The ray after entering into the second medium, that is a denser medium in this diagram, is the refracted ray. Here the red dotted line, what is that? That red dotted line is the actual path of the incident ray. If the denser medium is absent, the incident ray coming with a speed v1 would have passed through this path. So that is indicated by this red and dotted line. So here the refracted ray is not along the red dotted line, but it is in some other direction. Actually, it has bent towards the normal. Note this point. The light ray, when enters from rarer medium to denser medium, it bends towards the normal. Okay. Now, let us move to the next picture. Here, in this picture, the light ray is coming into rarer medium from denser medium. So here green part is the denser medium and white portion is the rarer medium. The light ray is originally in denser medium. Then it touches the interface. Then instead of passing through the straight path, what is the straight path? If there is no change of medium, the light ray would have traveled through the red dotted line, but it is not happening. As the medium has changed, the incident ray just after entering into the next medium, that is a rarer medium, it has taken some other path. Here it bends away from the normal. So when a light ray moves from denser medium to rarer medium, it bends away from the normal. Note this point. Look at this picture. So it is a light ray is incident on the interface. A red dotted line indicates its path in the absence of change of medium. So the light ray has bent towards the normal. So its direction is changed because the medium has changed. And dotted black line is the normal. So the angle between the normal and the incident ray is the angle of incidence, and it is represented by letter I. Once again, the angle between the normal and the incident ray is the angle of incidence, and it is denoted by the letter I. Then in this green part, the angle between the normal and the refracted ray, the angle between the normal and the refracted ray is the angle of refraction, and it is represented by the letter small r. Okay. This is rarer medium. Speed of light here is v1, and this is denser medium. Here speed of light is v2. v1 is greater than v2. This is the line separating the two medium. This is called interface. This is incident ray, and the point where the ray touches is the point of incidence, and this is normal drawn at the point of incidence to the interface. This is refracted ray. The angle between the incident ray and the normal is the angle of incidence and is represented by letter I. This angle between the normal and the refracted ray is the angle of refraction and is represented by the letter R. This is one medium. This one is second medium. Suppose this is rarer medium and this one is denser medium. This is rarer medium and this is denser medium. Here speed of light will be greater in the rarer medium, and here speed of light will be slower in the denser medium, of course, comparatively. This is our light beam. These three lemons represent three light rays. It is difficult to get one single light ray. Always we are using a light beam which is a pack of thousands of light rays. So from the beam of light in which there are some hundreds of light rays. For demonstration purpose, you assume these three lemons as three light rays of a beam. This beam of light consisting of three light rays is approaching the interface. So this is one medium 1, this is medium 2, and in between is the interface. So when this light rays approach the interface, observe here, the first one has first reached the interface, whereas the third one is somewhere here. As this is denser medium, you can assume some Fevicol is spread here. This is a smooth one, this is a Fevicol spreaded area. So this one becomes slow because of the denser medium. In practice, you can use Fevicol here, or you can assume this is a denser medium and the speed of light is low. So as the speed is lower, this is still in rarer medium, this is in denser medium, this will be slower and this will be at higher speeds. So here a bending takes place like this, bending takes place. So in the concentric circles, this will be covering a maximum distance. So when it enters from one medium to other medium, that is rarer to denser, bending takes place. Bending takes place. So once this is completely entered into the other medium, it will continue a straight line path according to the speed in that medium. So here is the normal, entered this way, and bending takes place towards the normal. Okay, to give the minimum distance to one and the maximum distance to the other, bending takes place. This is the refraction of light. Now assume that the beam of light is moving from denser medium towards rarer medium. So this is denser medium. The beam has approached the interface. This one is first entering into the rarer medium, where this is a smooth surface. It can roll easily, so it will cover a maximum distance. This will cover a maximum distance, whereas this one covers a minimum distance because it is still in denser medium. So to have minimum distance to this one, maximum distance to this one, this will be rolling and later it will be continuing in a straight line. So whenever a light ray travels from denser medium to rarer medium, bending takes place and it is away from the normal. So bending away from normal takes place. So this is refraction of light. Okay students, hope you understand the phenomenon of refraction and bending of light at the interface of two different medium. Now my question is, what happens when the beam of light enters normally onto the interface? So type your answers in the comment section. Okay students, we discussed about the refraction of light. When a light ray passes from one medium to other medium, it suffers a deviation. So its direction is changed, and that change of direction is due to change of medium and due to change of speed of light. Then the extent of the change in direction that takes place when a light ray propagates through one medium to another medium is expressed in terms of refractive index. What does it mean? Suppose few students are playing a long jump. One jumps to a distance 3 meters, other one 3.1 meter, then 3.3 meter, then 3.5, like that. To have a comparison who is great and who is superior among the students, you will be deciding by the distance, by how much distance he has jumped. Whoever has jumped a maximum distance, that number decides his superiority. Similarly, in the refraction of light, when a light ray passes from one medium to other medium, it deviates, it changes its direction. The ability of a medium to change the direction of light is measured in terms of refractive index. So, refractive index is a number which indicates the bending nature. One medium bends a light a little bit, and the other may bend the light by some extra angle. So, someone may bend maximum. Like that, when we compare the property of bending of different media, the ability of bending is different for different media. And this ability of bending a light ray by a medium is expressed in terms of refractive index. Okay, right. Before we give a definition to this refractive index, first of all, let us have few things. Light travels in vacuum with a speed 3 into 10 to the power of 8 meter per second. So speed of light in vacuum is 2.99 something. We will write as 3 into 10 to the power of 8 meter per seconds. And this speed is the maximum speed. No rocket, no vehicle can achieve a speed which is greater than speed of light. And speed of light in vacuum is the maximum possible speed in this universe, and its value is 3 into 10 to the power of 8 meter per second, and it is represented by a letter C. So we can write C is equal to 3 into 10 to the power of 8 meter per second. Okay, speed of light in vacuum represented by letter C is equal to 3 into 10 to the power of 8 meter per second. Now, take any one medium like water, glass, diamond, mica, ruby, flint glass, ground glass, etc. etc. Any medium through which light can pass is called transparent medium. Take any one transparent medium, and speed of light in that medium is V. Of course, meter per second. As we already discussed, speed of light in vacuum is represented by C, and its value is 3 into 10 to the power of 8, and it is the maximum value. Therefore, V must be less than C. V is definitely less than C. Speed of light in a medium is always less than speed of light in vacuum. So, for sure, V is less than C. Right. Since V is not equal to C, it is less than C, you can express V as a part of C. A part of C. So, the absolute refractive index of the medium is defined as the ratio of speed of light in vacuum to the speed of light in medium, and is represented by letter N. The absolute refractive index of the medium is equal to speed of light in vacuum divided by speed of light in the medium. So we use the symbol N for absolute refractive index, and symbol for speed of light in vacuum is C, and speed of light in medium is represented by V. So we can write N is equal to C by V. N is equal to C by V. So N is a refractive index, C is a speed of light in vacuum, and V is speed of light in medium. So this is the formula or definition for absolute refractive index. Because the right hand side is the ratio, and the numerator and denominator both are speeds, both has same unit, meter per second. So N is equal to C by V, and C is expressed in meter per second, V is also expressed in meter per second. So absolute refractive index has no units, it is just a number only. Here in the formula N is equal to C by V, N and V are inversely proportional to each other. Here C equal to 3 into 10 to the power of 8 meter per second is a constant. Numerator C is a constant. So N is proportional to 1 by V. You can say refractive index n is inversely proportional to speed of light in the medium. That means more the speed, less is the refractive index. Less is the speed of light, more will be the refractive index of the medium. So let us go for an example. Already we know speed of light in vacuum C equal to 3 into 10 to the power of 8 meter per second. And given that speed of light in glass V is equal to 2 into 10 to the power of 8 meter per second. So it is given that speed of light in vacuum is 3 into 10 to the power of 8 and speed of light in glass is 2 into 10 to the power of 8. So refractive index of glass is to be determined. Formula is N is equal to C by V. Absolute refractive index is the ratio of speed of light in vacuum to the speed of light in medium. N is equal to C by V. Substitute the values. N is equal to, in the numerator 3 into 10 to the power of 8 and in the denominator 2 into 10 to the power of 8. On cancellation of 10 power 8 and 10 power 8, you get N is equal to 3 by 2. So the refractive index of glass is 3 by 2. Here we have a table. Refractive index of few material media is tabulated. Index is for singular, indices is used for plural. The refractive index of air is 1.003. It is almost equal to 1. So refractive index of air is equal to 1, and in general we say refractive index of vacuum and air are equal and it is equal to 1. Then the third one, refractive index of water is 1.33. Then the refractive index of crown glass is 1.52. Then the refractive index of flint glass is 1.65 and refractive index of ruby is 1.71 and refractive index of diamond is 2.42. So refractive index of diamond is maximum, that means bending nature will be maximum in diamond. Case 1. Light ray passing from air to water. Here air is the rarer medium, its refractive index n is equal to 1, and water is the denser medium, its refractive index n equal to 1.33. This is the incident ray, this is normal, and this is the refracted ray. So light ray bends towards the normal. Now case 2. The rarer medium is air, n is equal to 1, and the denser medium here is diamond, whose refractive index n is equal to 2.4. It is greater than water. The incident ray, the normal, and this is the refracted ray. So the light ray bends more towards the normal. In case 1, we got bending of light ray in water. As light enters from rarer to denser, bending towards normal takes place. And in case 2, the light ray enters into diamond. Here also bending takes place, but n is equal to 2.4 is greater than n is equal to 1.33. That is, refractive index of diamond is greater than refractive index of water. Therefore, bending in diamond is greater than bending in water, because refractive index of diamond is greater than refractive index of water. So 2.4 is greater than 1.33. That means refractive index of diamond is greater than refractive index of water. Therefore, bending of light in diamond is greater than bending of light in water. Okay, right. So let it be rarer medium, and for air refractive index n is equal to 1. This is the incident ray, and this would be the path when there is no change of medium. Water is the denser medium. This will be the refracted ray. If glass is the denser medium, this will be the refracted ray. And if ruby is the denser medium, then this could be the refracted ray. And if diamond is the denser medium, then this will be the refracted ray. So conclusion is, more the refractive index of the denser medium, more will be bending of light ray. Okay. Refractive index depends on the following factors. Number one is nature of material, and number two is wavelength of light used. Already we discussed about refractive index of various media for air, water, glass, diamond, etc. The refractive index of various materials depends on the nature of the material. For example, refractive index of air is 1, for water it is 1.33, refractive index of ground glass is 1.52, refractive index of diamond is 2.42. For different materials, different refractive index values are there. And the second point is refractive index depends on wavelength of light. So for example, water has a refractive index 1.33. If you use yellow color, if you do experiment with yellow color, blue color, red color, like that, depending on the color you have used, depending on the wavelength of the light you have used, the refractive index of the same medium, the same water differs. Instead of 1.33, it becomes 1.34, 1.35, 1.39, like that. The value of refractive index changes with respect to the color of light we are using. Color means wavelength of light we are using. As an example, the refractive index of glass is 1.5. For yellow, if it is 1.5, for red, it will be 1.55. Then, comparison of refractive index, that is relative refractive index. Relative is nothing but comparative. Relative refractive index. When refractive index of one medium is compared with the refractive index of another medium, it is called relative refractive index. For example, refractive index of air is 1 and refractive index of water is 1.33. Refractive index of glass is 1.5 and refractive index of diamond is 2.4. So, when compared to water, the refractive index of diamond is almost double. So, relative refractive index of diamond is approximately equal to 2. That means double to that of refractive index of water. So, we can say relative refractive index of diamond is 2 when compared to water. Okay. So, relative refractive index of a medium is defined as refractive index of one medium divided by refractive index of another medium. Let us discuss clearly. Refractive index of second medium is equal to N2. Refractive index of first medium is equal to N1. That means absolute refractive index. Refractive index of second medium with respect to first medium is given by refractive index of second medium divided by refractive index of first medium. In symbols, N21 is equal to N2 by N1. The refractive index of second medium with respect to first medium is represented by the symbol N21. Here N means the general meaning of a refractive index. This suffix 21 represents for the medium 2 with respect to medium 1. For the medium 2 with respect to the medium 1. I repeat, for the medium 2 with respect to medium 1. So, refractive index of second medium with respect to first medium is represented by N21. So, the formula is N21 is equal to N2 by N1. N21 is equal to N2 by N1. Now, let us substitute the formula of absolute refractive index formula that we have already discussed. Absolute refractive index of second medium N2 is nothing but C by V2. And similarly, absolute refractive index of first medium N1 is equal to C by V1. Then substituting N21 is equal to N2 by N1, that is equal to C by V2 whole divided by C by V1. On cancellation, CC gets cancelled. we get 1 by V2 whole divided by 1 by V1. That can be rewritten as V1 by V2. So finally we got N21 is equal to V1 by V2. N21 is equal to V1 by V2. So relative refractive index of second medium with respect to the first medium is equal to ratio of speed of light in first medium to the speed of light in the second medium. N21 is equal to V1 by V2. So we got two formulas here. N21 is equal to N2 by N1 directly from the definition, and on simplification we got one more formula. N21 is equal to V1 by V2. Then based on these two formulas, by using common sense, let us define relative refractive index of first medium with respect to second medium. Relative refractive index of first medium with respect to second medium. That means just interchanging the media. In place of 1, write 2. In place of 2, write 1. So we get N12 is equal to N1 by N2. N12 is equal to N1 by N2. And N12 is equal to V2 by V1. Okay, right.